I feel that you have been shortchanged probably in your entire education because you might have read on the internet that there is a thing called chaos. But what is chaos? So I want to teach you chaos in one lecture. So another famous mathematical method lecture when a semester is covered in hour and 20 minutes. So I will teach you what Bernoulli map is, and this is the essence of deterministic chaos. The way I have to teach it is following Goethe's Faust. Mephistopheles is a graduate student at the beginning of the Faust. He tells Faust, who is the teacher, the master, you always have to say it 3 times. So I'll say it first time, and the second and third time you'll have to find elsewhere. First time is, what is chaos? It's coin toss. Here is the old-fashioned way they teach you about chaos in old-fashioned institutions. It's like, nothing has happened since 18th century, and we think about everything. Space is frozen, time is evolving. So it's time evolution formulation, which is kind of intuition you have about the world, but it's not a deep insight into how the world actually works. You would like to have something that with probability 1/2 gives you either heads or tails. And Bernoulli has invented, one of the famous brothers, Bernoulli has invented a simple map that does the job. So if you have initial state of your system called xt in a unit interval between 0 and 1, you have a rule that if you are in the first half of the unit interval, you just multiply that number by 2. It's natural to even write it in binary, then it's totally obvious what's going on. And what it means is that I start with tail, and I flip the coin, and I can end up either with head, tail, or head, any place on unit interval. So that's what this factor 2 does. If you try to pull the trick on the second half of the interval, 2 times anything larger than 1/2 would throw you out of the interval, so this is not good. So Bernoulli says, take modulo 1, meaning remove the integer part. And that's what this second branch of this map does. So the way this works, this game, is that the world is divided in 1 step in 1/2. In 2 steps, it's divided into 4 intervals. So everybody in this little interval stays in the first half for 2 steps. Everybody who is on this side, ends up on the right-hand interval under this map, and so on. And if you want to, you can notice that there are special points in this state space, as we call it. Your state is anybody whose height is between 0 and 1, let's say 6 feet in units of 6 feet. If you're a dwarf of height 0, you will remain dwarf forever. But if you're of the height, this particular height, what will happen to it next year, you'll be bigger, and next year after you'll be smaller, and you just run around on what's called a 2 cycle. So it turns out this world has special solutions that don't go anyplace. They just run on so-called periodic orbits. And it's a model. It's not really coin toss, because coin toss, you can model it, and it's a hard calculation to do a real coin. But it has the same property that it describes something that looks like a probability if you do tabuada to your data set, which is you take 1,000 iterates of some random initial point, some natural number. And you'll find out that half of them are less than half, and half of them are larger than half. So that's the essence of deterministic chaos. It's something that has precise law of nature, just like Newton equations or Zangwill's equations, also called Maxwell's equation, precise. They give you unique outcomes. But it has this particular property which is called chaos. And what is chaos? To understand that, let's rethink what's modulo 1, what you mean by that. You have this rule now that says if I have a unit interval, I multiply every point on it by some number, which is 2 or larger. Let's make it integer to make it simple. And what happens is things that are unit interval now are in interval, which is here called stretching factor, let's say 2 or 3 or 5 or 6. And to make this thing run around and being able to keep throwing your coin over and over again, what you do is you subtract the integer part. So you take this number here, subtract the integer part, and you make sure that the thing I'll call phi to suggest a field, you'll see why, like Maxwell field, in such a way that at every step you subtract this integer to ensure that the result is still in the unit interval. We have two things happening in time. You have the set of possible values they can take, modulo of this is up to s minus 1. That's the largest integer you can take of something that's multiplied by s. So there is an alphabet and there is a field at every instant in time. So for example, if you want to model a dice throw that has 6 possible values, and Bernoulli says, the thing that will look like a dice throw will be something where I take unit interval, I stretch it by factor 6, and then I slice it tuk, 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 with my integer alphabet. And my space of initial condition gets split into 6 intervals, which are labeled by this symbol, these subintervals. And now I can keep throwing this, and that will have the same probability distribution after many throws and tabuada measurements done on the data, as though I was throwing a real dice with 6 faces. So, what's chaos? The main thing that happens in this kind of system is when you look at two very close initial conditions. So I try to throw my dice in a really clever way, which means I start with some initial condition here, and I try to have a predetermined future. So I cheat. For example, I want to get 6s all the time. So I make sure that I have initial condition that just produces 6s. And, I have, 5, 5, 5 in this labeling corresponding to the 6th face. And what happens is, because this is a stretching, the neighboring points get multiplied, the distance gets multiplied by 6 every time. So every trajectory is unstable because its neighbors are just running away like crazy. And the distance to the neighbor is multiplying by 6. So, when I start with a little one-dimensional cigar of initial conditions, everybody runs away. And the rate of how you run away per iteration is obtained by taking a logarithm. So that's called rate at separation, logarithm of the stretching factor. And it has a fancy name. There was a Russian nobleman called Lyapunov, and he was positive. So chaos means that everybody is unstable. You quantify this by computing local instability or logarithm of how you separate. That's called Lyapunov. And if positive, Lyapunov is a positive number, it means you have local instability. Now, usually local instability would mean you just explode like a hydrogen bomb, separating by factor 6 at every instant in time, anytime you take a picture. But here, we want to keep playing this game, so that's why we took modulo 1. And now we have distinct possible futures. Each one of them is labeled by this sequence of symbols. This is what could have happened. I could have been jumping between intervals using this map, following the symbols. And the number is, in this particular case, 6 to the n after n steps. And that I think of number of configuration, number of distinct walks through the state space of the system. And I can also compute the rate in which the number grows at every time by taking a logarithm of the total number of outcomes and dividing it by n. And that in deep ways is actually connected to statistical mechanics. That's called entropy, meaning the logarithm of number of possible configurations. If that is positive, then we have chaos, meaning all neighborhoods fall apart, center cannot hold, but we are contained in a unit interval. We cannot escape. So we keep running around, and this entropy counts the ways of numbers I can come back to my neighborhood. There are distinct ways. There's so many of them. So that's deterministic chaos. Any system that has these two properties, locally unstable and globally coming back in exponentially many ways, that's a chaotic dynamical system. And even though it's mechanical, I can make a perfect dice or perfect coin, I can throw it infinitely many times in a perfect world, still I would get probabilities, because the moment I have an initial bunch of conditions which are not infinitely precisely specified, I get myself in this situation. And in the physical world, not Platonic world, we can only prepare things with finite precision, and we can evolve them with finite precision. So chaos rules.